We now consider standing waves. A standing wave occurs when there is constructive interference between two waves at the same resonant frequency but traveling in opposite directions. So consider a wave like this traveling in this direction, which maybe we could call wave F1. And then there's a second wave that could in fact be going like this, or maybe it's upside down, but the key thing is that it is traveling in the opposite direction. So there's this and there's that. Now if you look at those two waves, the total velocity, if they're identical waves, is actually equal to 0. So the total velocity is 0. And this is why it's standing. There's motion this way, but there's an equal disturbance of motion moving the other way, which leads to a very interesting situation in which what we have is a wave that goes up and down, oscillating like this, but which has these peaks. Not a very good drawing, but I'll show you one in a second. These peaks do not have any motion. So peaks will oscillate, but the disturbance doesn't propagate. Now, how do we get these two waves that have the same resonant frequency but which are traveling in opposite direction? Well, one of the most common ways to get the second wave traveling in opposite direction is by reflection off a barrier, or maybe I should say interface, between two media. Now, we've already talked that when a wave hits an interface between two different media, some of the wave can be reflected, and potentially all of the wave could be reflected, depending on the nature of the interface. An example of this is a bound string. So for instance, you might have a table here and have some sort of a pulley and have a string on one side, and then on the other side of that string, on the other side of that pulley, you have a mass here, and you have a string attached. For instance, that string might be propagating because there's a motion this way it hits the end here where it's bounced, and it gets bounced back. So you have a bound string. That's one way to create this sort of thing. And now I will show you an example of that with a video. Look at the peaks shown in green and the nodes shown in red. While they oscillate up and down, they do not propagate horizontally. Here we see in slow motion, notice the oscillation of the peaks, but no propagation. All motion is up and down. For the wave shown in the video, the right traveling wave or incoming wave going in this direction, which we'll call the positive x direction, and we'll say that this is x equals 0, and this distance to the pulley is x equal L. For that wave going toward the pulley, traveling in the positive x direction, can be written as f1, a function, is the amplitude times the sine of kx minus omega t. When the wave hits, it is reflected, and we get a minus sign, followed by a sine kx plus omega t, where the positive sign right here indicates that it is a negative x traveling wave. That is, it's traveling to the left. Now, to find the total standing wave, one has to now go and add these two waves together. This represents somewhat of a difficulty. I show in another video how to do that mathematically, but in this video I'll just use the results. When you add the two waves together, you get minus 2 times the amplitude of any one wave times the cosine of omega t. This term here, 2a cosine omega t, is an amplitude that varies from 2a, when the cosine omega t is equal to 1, to 0, when the cosine of omega t is equal to 0, that is, omega t is pi over 2. Then it's multiplied by the sine of kx, which is the space part. Notice that the time part and space part have been separated. So when you're looking at the wave on the string, you're looking at the spatial part, and you see a sine function. The cosine part with time is what you're seeing as it vibrates up and down with changing amplitude. So because you just have a sine of kx with no omega t in the argument, it is a non-moving wave. Now, a string that is bounded on the end, like what we have, has certain boundary conditions that it has to meet. And among those things about that boundary condition is the fact that not all frequency or wavelengths are allowed. So, not all wavelengths are allowed, and hence not all frequencies are allowed given a given wave speed, that is, for a given mass per length string with a given tension. The wavelength is therefore said to be quantized. Quantization is something that shows up often in classical physics. It also shows up in a new type of physics called quantum mechanics that describes how atoms and other things that are bound behave. This quantized wavelength, which means it has discrete values, those values are called eigenvalues in mathematics. The word eigen is German for proper, meaning that only some answers are proper or allowed and others are not. The longest wavelength is twice the distance between the two supports. So if the pulley to the support is 1 meter, the longest wavelength that this string will handle is 2 meters. We can write that as 2 times the length divided by 1, where 1 is the number of peaks. Now, shorter wavelengths are also allowed, so it is possible to have other types of waves, that is, waves that have a smaller wavelength, and in general what we can say is that the wavelength for an allowed wave on this string is 2 times the length of the string divided by the number of peaks. So if you have 3 peaks, the wavelength is 2L divided by 3. If you see 4 peaks, the wavelength is 2L divided by 4. In the video, I'll show you that by changing the frequency that I put into the system for a given speed of the string, of the wave, I'll get different wavelengths, and you will see each of these humps, and you can determine what the wavelength of the wave is. We have 2 peaks, 3 peaks. See the peaks moving up and down. Now we have 4 peaks. Notice how the amplitude decreases as the energy is spread out into more parts of the wave. Now we have 5 peaks. Associated with the longest wavelength is the lowest frequency. This frequency is called the fundamental frequency, or the first harmonic. Its frequency is given by the speed of the wave, which depends upon, in this case, the mass per length and the tension, divided by the wavelength, which is determined by the boundaries, which in our case is 2 times the length. So F1 is equal to the speed of the wave divided by 2 times the length. And the 1, which is the number of peaks, is in front. The next lowest frequency that you can have is called the second harmonic. And the second harmonic is sometimes also called the first overtone. Now, you can think of the overtones as always 1 less than what you have for the harmonics. So if you have a third harmonic, you will have a second overtone. Okay? Now the formula for that is again found by the speed divided by the wavelength. So our wavelength here is 2L divided by 2, where 2 indicates the number of humps, peaks, and that's the same as the harmonic number. So it's V divided by lambda 2, but lambda 2 is 2L over 2, so you get V over L, which is twice the frequency that we got for the fundamental frequency. So if you had the nth harmonic, to find it, you just take the fundamental frequency of the instrument or string and multiply by n, where n is the number of peaks. And remember, that will be the n-1 overtone. So the 10th harmonic would have 10 times the frequency of the first harmonic, the fundamental frequency, and it would be called the 9th overtone. All right, that's all there is for this discussion of standing waves.